Hello everyone. Today we will discuss about the configuration space and transformation of coordinates from one system to other system. Those will be r and theta. If I draw a line from O to P, then you know that it becomes r, and theta is the angle rotated by line OP from the x-axis in anti-clockwise direction. Right? So what is the relation between Cartesian coordinates and the polar coordinates for two-dimensional space for a point which is placed at P? You know very well that x is equal to r cos theta and y is equal to r sin theta. Here x and y are the Cartesian coordinates, r and theta are the polar coordinates. Here the other relation which you can have, that will be x square plus y square is equal to r square, and the tan theta is equal to y upon x, or theta is equal to tan inverse y upon x. So here you can see that there is a transformation of the Cartesian coordinates towards the polar coordinates, right? Because here you see that the one polar coordinate theta can be written in Cartesian coordinates, and the other is that you can write your r in terms of the, and the polar coordinates can be can be written in terms of the Cartesian coordinate system. Here we have considered a two-dimensional case. Similarly, example is that the spherical coordinate system. Again, in a spherical coordinate system, suppose this is the origin and this is your x-axis, this is your y-axis, this is your z-axis, and there is a point P. Now to define the spherical coordinate, we will write here, let us say the distance between O and P is r, and you know that P will have the Cartesian coordinates x, y, z, and in terms of the spherical coordinate system, the point P will have the coordinates r theta, spherical coordinates r theta and phi. Theta is the theta is the angle made by OP with the z-axis. This is your theta, and suppose it is the line OM. Now if you see here that your OP is equal to R, then it will have a component along the z-axis that will be equal to r cos theta. So here first I will complete the diagram. Let us say this is your this distance is your x, and this distance is your y, and this distance is your z, because this is this line is parallel to this line. So if this angle is your theta, so this will be your angle theta, alternate angles. So here you can write here that your z will be equal to r cos theta. Now you know already that your OM is equal to it is your r sin theta. I have already discussed it. Now let us say that OM is making an angle of phi with the x-axis. So here your x becomes, because it is r sin theta and this angle is phi, so it will have a component that will be r sin theta cos phi, and that is equal to x. This is the r sin theta, and this angle is phi. X and y are perpendicular, so this angle will be 90 minus phi. So your y, you already know that it becomes r sin theta sin phi. So here you see that you have written here the Cartesian coordinates in terms of the spherical polar coordinates. We can find some relations between the Cartesian coordinates and the spherical polar coordinates from these equations. If you see here that from this equation and from this equation, you can write your x square plus y square is equal to r square sin square theta, right? So here your r sin theta is equal to root x square plus y square, and from here you know that your r cos theta is equal to z. So from here you can find tan theta is equal to root x square plus y square upon z. Similarly here your theta, you can write theta in terms of tan inverse root x square plus y square upon z. Now if you square of these three terms, then you can find a relation also like that your r square is equal to x square plus y square plus z square. The other relation you can find here, if you see these two equations again, that your tan phi is equal to, it is equal to y upon x, or your phi is equal to tan inverse y upon x. So this is one relation, this is the one relation, and this is also a relation. So here what is actually I want to explain you that here we can write the Cartesian coordinates in terms of the spherical polar coordinates r theta phi y r theta phi and z is equal to z r theta phi. Similarly, we can write your spherical polar coordinates in terms of the Cartesian coordinates. Your r will be r x y z. You can write theta in terms of the x y z, and you can also write phi in terms of the x y z. At least you can make some relations between the Cartesian coordinates and the spherical polar coordinate system. So that is how we can transform one coordinate system to the other coordinate system. Now we will discuss the configuration space. This is very important to understand that how you define the configuration space in classical dynamics. To define the configuration space, let us assume that there is a point placed in three-dimensional space. This is the origin, this is your x-axis, this is your y-axis, this is your z-axis, and there is a point. First I will, before taking this example, I will take some other examples. Now I am saying that suppose it is a wire and an object is placed here, right? So at any time this object will have, if we have to specify the position of this object, then we will require only one coordinate. If this wire is along the x-axis, then you will require a coordinate x, and if this wire is along the y-axis, then you will require a coordinate y, and if this wire is along the z-axis, then you will require a coordinate z. Or you can say here that for this system you require only one coordinate, right? Now suppose there is a two-dimensional space, and this is your x-axis, this is your y-axis, it is origin, and suppose there is a point P space. You know that this point in Cartesian coordinate system, it will have two Cartesian coordinates x and y, right? I am saying the other thing, that suppose a particle having two Cartesian coordinates, you know that you will have to specify its position, or you will require two coordinates, one is x-axis and other is y-axis, right? Now I take the third example. Suppose there is a point P in three-dimensional space, and it is a Cartesian coordinate system. So your point P will have the three coordinates x, y and z. You clearly know that if we have to specify the position of the point P in three dimensions any time, then P will have the Cartesian coordinates x, y and z. If I say that let us say there is a point, I say this thing in other way, that if a point having the coordinates, Cartesian coordinates x, y and z, then if you have to specify the position of this particle, then you know that you will require three coordinate axes, right? Now Suppose there are two particles in three-dimensional space. This is your x-axis, this is your y-axis, and this is your z-axis. So this is 1 point and this is 2 point, right? Let us say it has the coordinates x1, y1, z1. It has the coordinate x2, y2, and z2. So if you have to specify the position of this dynamical system, then you know that you will require the 6 coordinates, and those will be x1, y1, z1, and x2, y2, and z2, right? Now this is very important to understand that suppose I am considering this 2-point system as a single point system, and if this single point system has these 6 coordinates, those are x1, y1, z1, x2, y2, z2, then now you have to think that here let us say it is a point P, the 2-point system, we have replaced this 2-point system as a single point system, but still it is having 6 coordinates x1, y1, z1, x2, y2, z2. Now if you have 6 coordinates x1, y1, z1, x2, y2, z2, then if you have to specify the position of this single system, clearly you need 6 coordinate axes. So this 6 coordinate axis is called as the 6 coordinate axis space is known as the configuration space or phase space. It is also important that when the 2-particle system is replaced by 1-particle system, it is not necessary that the 1-particle system will either will be at point 1 or it will be at point 2. It may be somewhere in a 6-dimensional space. So that 6-dimensional space is called as it is called as the configuration space or phase space. x1, y1, z1, x2, y2, and z2. Thank you.